Hello warriors, this is Miss Lemons, and today I'll be walking you through electrons in the atom, specifically focusing on waves and light. Now before we begin this video in PowerPoint, it's important that you have your introduction to electron energy and light packet out, or your worksheet out. We're going to be filling this in as we go through the video. You should also have this first page completely done. So if it's not done, make sure you pause the video and complete that on your own. All right, let's get started. So, the essential question, how can the movement of electrons impact the energy of an atom? Before we get into the nuts and bolts of the energy of electrons, let's talk about the anatomy of a wave. Now, you should have already viewed a video that talks about the parts of a wave, but let's just review them. So, the top of the wave is called the crest. Bottom of the wave is called a trough. A wavelength is either from crest to crest, trough to trough, or equilibrium to equilibrium. If you have a wave that starts at equilibrium, it can be kind of difficult to see where the wave starts and where the wave ends. So let me show you how you can count the number of waves if it starts at equilibrium. If it starts at equilibrium, you want to make sure that you have one full crest, one full trough, and then start back where you started at. So in this image, we have 1, 2 waves. So there are 2 wavelengths in this picture. The last term you should be familiar with is frequency. Frequency is how frequently a wave occurs over a period of time. So waves are characterized by 3 variables: frequency, wavelength, and energy. We're going to learn how to calculate all 3 of these variables, and we're also going to learn the relationships between these variables. This right here is the electromagnetic spectrum. All light waves are electromagnetic waves and are therefore plotted somewhere on this spectrum. So let's kind of walk through this picture, this chart. The first thing I want to point out is wavelength in the upper left-hand corner. Wavelength is always measured in meters when we're calculating it. You can see here that we have a variety of different waves. We have radio waves. Yes, the same radio waves you use to listen to the radio. Microwaves, infrared rays, those are waves. Those are going to be the heat lamps. Visible waves, ultraviolet waves, X-rays, and gamma rays. So as we move left to right on the electromagnetic spectrum, you can see that the wavelength decreases. And you can support that by looking at either the powers of 10, which decrease as you move left to right, or you could just look at this picture and see that the wavelength itself is getting shorter and shorter and shorter as you move left to right. The other thing I want to point out is energy. As we move left to right on the electromagnetic spectrum, energy increases. So as wavelength decreases, energy increases. Energy is measured in joules, which is denoted with a capital J. Frequency is the last variable that we use to describe electromagnetic waves. Frequency is measured in hertz, and as we move left to right on the electromagnetic spectrum, frequency increases. Now remember, frequency is how frequently a wave occurs in a certain period of time. You can see that frequency increases by either looking at the power of 10 and how it increases, or you can look at the image given to you. As we move left to right, you can see that waves happen more frequently, even though the wavelength is getting shorter. It's also important to point out that the little sliver in the center of the electromagnetic spectrum is the visible light spectrum. Humans can perceive visible light. This is what we see as color every single day. And it is the only part of the electromagnetic spectrum that we can see. So you do have to remember the order of the electromagnetic waves. So going from largest wavelength to smallest wavelength, you can use this memory trick. Raging Martians invaded Venus using X-ray guns. I know it's kind of silly, but hopefully it's a memory trick that will help you remember the order of electromagnetic waves. So frequency, denoted by a lowercase f, is the number of waves that pass through a certain point in a given time, and we measure frequency in hertz. If a wave has a small frequency, that means it has a large wavelength. If we have a large frequency, that means we also have a large energy. So if you look at these two waves here, in this top wave, we actually have 1, 2 wavelengths, and it's happening less frequently than the waves underneath. Here we have 1, 2, 3, 4 waves. So this is happening more frequently, but the wavelength is smaller. The top wave is happening less frequently, and the wavelength is larger. As far as energy goes, if a wave happens more frequently, it's going to be interacting with the medium it's in more frequently, putting more energy into that medium. So as wavelength increases, frequency decreases. This is known as an inverse proportion. As one variable increases or goes up, the other variable goes down. As energy increases, frequency also increases. This is called a direct proportion. As one variable goes up, the other variable also goes up. Okay, so the electromagnetic spectrum, if we zoom in on the visible light spectrum, you can see that we have all hues of colors. So the highest end, the largest wavelength, is going to be red. So red has the largest wavelength, which means it has the smallest frequency and the smallest energy. Violet, on the other end of the electromagnetic spectrum, the visible section, has the smallest frequency, the smallest wavelength, the largest frequency, and the largest energy compared to the other colors in the visible spectrum. All of the colors in the spectrum have their own wavelengths. So when we're talking about the equations, there are two equations we are going to be dealing with. The first one is called the wavelength equation, and it showcases the inverse relationship between wavelength and frequency. So let's go ahead and label each of these variables with a name and a unit. The first variable listed is c, lowercase c. It is the speed of light in a vacuum. This is a constant, and it's given to you. It's measured as 3.00 times 10 to the 8th power meters per second. The lambda is wavelength, and we measure that in meters. I do want to point out briefly that on the previous slide, we looked at red and violet light measured in nanometers. So even though the values are given to us in nanometers, when we're doing these calculations, we can't put nanometers into them. We have to convert it into meters first, then put it into the equation. Finally, the lowercase f stands for frequency, which is measured in hertz. It's important to note, too, that all light travels at the speed of light, which makes sense. That means that all light travels at the same speed. Please take a moment to jot that down in a different color somewhere on your paper. So, my super secret tip. If you have a math problem or a word problem that says anything about wavelength, you need to use the wavelength formula. Why? Because the other formula doesn't have wavelength in it. This formula is the only one that has wavelength in it. So the second formula you're going to be working with is the energy equation. This one describes the direct relationship between frequency and energy. The capital E stands for energy, and it's measured in joules. The H is Planck's constant. This is a constant, and it will be given to you. It's measured in 6.626 times 10 to the negative 34th power joule seconds. Finally, we have frequency, which we are already familiar with and is measured in hertz. Another tip of mine, if you have a math problem that says anything about energy, you're going to use the energy formula. Because again, this is the only formula that contains energy. The other formula contains wavelength. This one contains energy. So while you're doing your calculations, I'm going to be introducing you to the SUS method. If you are in my class, you might be familiar with the SUX method for dimensional analysis, and this is not that much different. We're not going to do any practice calculations in this video, but if you're interested in seeing me walk through those calculations, please chime into the other video that will be provided to you. So let's talk atomic emission spectra. You should be looking at skip past all of those calculations, and look at number 21. Before you start this section, read the paragraph above 21. All right, so we know a quantum is the amount of energy needed to move an electron. A quantum of energy is absorbed when an electron increases its energy level. Now this makes sense. If we want to get this electron in energy level 1 up to energy level 2, we have to push it up to that energy level. To push something uphill or up an energy level requires energy. So we have to put energy into the atom in order to move that electron. So put energy into the atom, you're going to push that atom or electron up to the higher energy level, and now we have an atom that's in its excited state. And this is because the electron has been pushed up to a higher energy level. A quantum of energy is emitted or released when an electron decreases its energy level. So think of this as the electron relaxing, releasing its energy, relaxing for the day and going back to its original energy level. When it does that, it releases energy. When that energy is released, and this is super important, when the energy is released, this is where the energy is converted into visible light waves. So release of energy or emission of energy from an atom is what produces the colored flames that we observe during the flame test. So it's important to note that during your flame test, you are not burning chemicals. You are heating up those salts, exciting electrons, and when the electrons relax, that's when energy is released in the form of colored flames. Once that electron relaxes, it's considered to be back in its ground state. And that's because it's returned back down to its original lower energy level. So a quick note about excited versus ground state. The excited state is whenever an electron is not in the energy level it's supposed to be in. The atom is then in its excited state. The ground state is whenever an electron is in the energy level it's supposed to be in, making the atom in its ground state. So if we look at these two orbital diagrams here of the same atom, this is 2, 4, 6. This is a carbon. It's got 6 electrons. But you can see that it's not following the off-bow principle, right? We skipped the energy level. We didn't fill it all the way up, and we just went right up to energy level 3. In the past, we've said that this is not okay. You can't do this. However, if you add energy into the atom, those electrons are going to be pushed up into higher energy levels. And so you would represent that by moving one of those arrows up into a higher energy level. If we were to draw carbon in its ground state, this is actually what it would look like. Another example showcasing excited versus ground state, you can see here that there are no electrons on energy level 1. And so there should be, stating by the off-bow principle, that we should start on the lower energy level, but we have an electron actually in the second energy level. When that electron comes back down to the first energy level, we end up having the ground state. So the image on the left is the excited state. The image on the right is the ground state. So some summary questions. If an electron moves from energy level 2 to energy level 4, Energy is absorbed. Remember, in order to go from a lower to a higher energy level, you need to push the electron up, and that requires energy. If an electron moves from energy level 4 to energy level 3, energy is released or emitted, like it's relaxing back to its ground state. So if we were comparing two transitions, an electron going from energy level 5 to energy level 2, or an electron going from energy level 5 to energy level 3, which transition would release or emit the most energy? It would make sense that the larger leap produces the most energy.